Physical characteristics of group 13 elements. Physical characteristics of group 13 elements. First occurrence. All elements are found in nature. All elements are found in nature. Boron does not exist in free state. Boron does not exist in free state. Exist in free state. Free state. Okay. Boron does not exist in free state. Okay. It is widely distributed in nature. It is widely distributed in nature. Widely distributed in nature in the combined state. In the combined state. Okay. Aluminium does not exist in free state. Aluminium does not exist. Aluminium does not exist in free state. But in combination. But in combination, it is widely distributed in nature. It is widely distributed in nature. Okay. It is obtained mostly from bauxite. It is obtained mostly. It is obtained mostly from bauxite. From bauxite. Okay. Bauxite Al2O3 into 2H2O. Okay. Remaining elements gallium, indium and thallium. Gallium, indium and thallium are rare elements. Okay. Second point, metallic properties. Okay. Second point, metallic properties. Okay. Metallic properties increases with atomic number. Boron is a non-metal, but aluminum, gallium, indium and thallium are metals. As a matter of fact, aluminum, gallium and indium show amphoteric, non-metallic and metallic properties, and only thallium is true metallic. Okay. Metallic property increases with metallic property increases with atomic number. Metallic property increases with atomic number. Metallic property increases with atomic number. Boron is a non-metal, but aluminum, gallium and thallium are metals. Boron are non-metals, but aluminum, gallium, indium and thallium are metals. Okay. As a matter of fact, aluminum, gallium, and thallium, aluminum, gallium, and indium so amphoteric. As a matter of fact, as a matter of fact, as a matter of fact, aluminum, gallium, and indium so amphoteric, so amphoteric, amphoteric. That means non-metallic and metallic. That means non-metallic and metallic non-metallic and metallic. Okay. Properties, and only thallium is true metallic. Properties. Non-metallic and metallic properties. Only thallium is true metallic. Only thallium is true metallic. Okay. True metallic. Only thallium is true metallic. Okay. Next point. Third point. Atomic and ionic radii. Atomic and ionic radii. Atomic and ionic radii. Okay. The atomic radii are shown in the order given below. Atomic radii. Boron is less than aluminum, equal to gallium is less than indium, are equal to thallium. This is atomic radii. Okay. The atomic radius of aluminum and gallium is nearly same. The atomic radius of aluminum and gallium is nearly same. This is due to d-block construction effect in gallium. Atomic number of aluminum is 13 and gallium is 31. Aluminum is 13 and gallium is 31. Okay. D-block elements scandium 21 and zinc 30 lie between aluminum and gallium. In D-block elements, electrons are filled in n-1 d to the power x ns2. The outermost shell ns is unaffected due to filling of electrons in n-1 d to the power x. Okay. Thus, variation in radius is small is that there is d-block construction. The increase in radius of gallium 4s241 due to increase in orbit is balanced by d-block contraction, and consequently radius of gallium is nearly same as aluminum. The increase in radius from boron to aluminum, and from gallium to thallium is due to increase in orbit number. The nearness in radius of indium and thallium is due to lengthened contraction effect in thallium. And moving down the group, the ionic radii of boron to thallium increases. This is due to increase in orbit number. Okay. And moving down the group, the ionic radii, of boron plus 3 to thallium plus 3 ion increases. This is due to 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 increase in orbit number. This is due to increase in orbit number. Increase in orbit number. Okay, numbers. The nearness in radii of aluminum plus 3 and gallium plus 3 due to d block contraction. The nearness in radii of aluminum plus 3 to gallium plus 3 is due to d block contraction and of indium plus 3 to thallium plus 3 is due to lanthanide contraction. Lanthanide contraction. Okay, fourth point. Point 4. Density, melting point and boiling point. Density, melting point and boiling point Density, melting point and boiling point. On moving down the group, density increases. Aluminum, however, has low density exception. Okay, and on moving down the group, melting point decreases up to gallium and increases again for thallium. Boron has three-dimensional covalent lattice and has very high melting point. Boiling point follows a more regular trend. And moving down the group, boiling point decreases. Okay, then on moving down the group, moving down the group, density increases. Aluminum, however, has low density exception. Okay, and moving down the group, density increases. Aluminum, however, has low density exception except for aluminum. Okay, and moving down the group, moving down the group, melting point decreases up to gallium. Melting point decreases up to gallium, and increases again for indium and thallium. Boron has three-dimensional covalent lattice and has very high melting point. Boron has Boron has high melting point. High melting point. Melting point. Boron has high melting point. Okay? High melting point. Boiling point follow as more regular trend. Boiling point follows. Boiling point follows. Boiling point follows a more regular trend. Follows a more regular trend. More regular trend, and moving down the groove. Moving down the groove, boiling point decreases. Boiling point decreases. Okay. Next point, electronegativity. Okay. Electronegativity. Next point, electronegativity. Next point, 5 point, electronegativity. Okay. Electronegativity. Next point, electronegativity. Okay. The electronegativity values of group 13 elements are comparatively low, and moving down the group, its value decreases from boron to thallium. Okay. The electronegativity value. The electronegativity values of group 13 elements are comparatively low. And moving down the group, its value decreases. From boron to thallium. Okay. Electropositive character. 6 point, electropositive character. Okay. Electronegative character. The electronegative values of group 13 elements are comparatively low. And moving down the group, its value decreases from boron to thallium. Electropositive character increases from boron to aluminum, but then decreases from aluminum to thallium. The increase in electropositive character from boron to aluminum is due to increase in size. However, gallium, indium and thallium are less likely to lose electrons. Hence, these are those less electropositive, and this is because of poor shielding by d electrons. Okay. Electropositive character increases from electropositive character increases from size is due to increase in size is due to increase in size. However, gallium, indium and thallium, however, gallium, indium and thallium are less likely to lose electrons, lose electrons. Hence these are those less electropositive, less electropositive. This is because of poor shielding, by the electrons. Okay. Electropositive character increases from boron to aluminum is due to increase in size. However, gallium, indium and thallium are less likely to lose electrons. Hence, these are thus less electropositive. This is because of a poor shielding by the electrons. Okay. Next point, 7th point, ionization energy. Ionization energy. Okay. Next point, ionization energy. Okay. Ionization energy. The trend of ionization energy is given as boron is the greater than aluminum, approx equal to gallium, and gallium is the greater than indium, and indium is the less than thallium. Okay. The ionization energy value do not decrease regularly down the group. Okay. The greater ionization energy of boron, from aluminum is due to radius effect. Radius of aluminum is greater than that of boron, and so ionization energy of boron is greater than that of aluminum. As the radius of aluminum and gallium is approximately same. Hence, ionization energy is also approximately same. The radius of thallium is slightly higher than that of indium. But ionization energy of thallium is greater than that of indium. Okay. This is due to higher effective number charge for thallium relative to indium. The poor shielding by d electrons and the resulting d block contraction affect the ionization energy values for the later elements. Okay. The first ionization energy of 13 group elements are lower than of first and second group elements. The outermost general electronic configuration of these elements is ns2np1. This is due to the fact that p electrons are less penetrating power than s electrons. Hence, s electrons are more tightly bound by the nucleus than p electrons. In case of first ionization energy, An electron is to be removed from the p orbital, where is second and third ionization energy. Electrons are to be removed from the s orbital. Hence, the trend of ionization energy as follows. Okay. Then first ionization energy. First ionization energy is the less than second ionization. First ionization energy is the less than of second ionization. Ionization energy is the less than third ionization energy. Okay. Nature of bond. The ionization energy of boron is so high that of beryllium. That of boron is always covalent in nature. Okay. The ionization energy of boron is so high. And nature of bond. Nature of bond. The ionization energy of boron is so high that of boron is always covalent in nature. Indium plus 3 oxidation state. Compounds are covalent oxidation state. Compounds are covalent in any hydrous state. Okay. The ionization energy of boron is so high that of boron is always covalent in nature. Indium plus 3 oxidation state compounds are covalent in anhydrous state, but ionic in hydrated form. Thus boron chloride and boron bromide and boron iodide and boron peroxide B2S6, AlCl3, gallium chloride and indium chloride and thallium chloride are also covalent. Ammonium AlCl3 into 6H2O is ionic as Al H2O 6 plus 3 into 3Cl negative indium plus first state. Thallium chloride is ionic. Indium plus 3 oxidation state. Oxidation state. The octet is not complete around the central atom. The octet is not complete. The octet is not complete around the central atom. Not complete around the central atom. Okay. There are only 6 electrons around the central atoms. There are 6 electrons around the central atom. Such compounds are electron deficient. Such compounds are electron deficient. In order to remove electron deficiency, in order to remove electron deficiency, such compounds show resonance are dimerized. Such compounds show resonance are dimerized are form complexes. Okay. Nature of bond. The ionization energy of boron is so high that boron is always covalent in nature. Indium plus 3 oxidation state compounds are covalent in anhydrous state but ionic in hydrated form. Thus, BF, VCl3, BBr3, Bi3, BTH6, AlCl3, GaCl3, InCl3, TlCl3 are also covalent. Aluminum AlCl3 into 6H2O is ionic as Al-H2O all 6 plus 3 Cl negative. In indium plus 1 state, thallium chloride is ionic indium plus 3 oxidation state. Okay. The octet is not complete around the central atom. There is 6 electrons around the central atom. Such compounds are electron deficient. In order to remove the electron deficiency, such compounds show resonance are dimerized. Dimerized are form complexes. Okay. Oxidation state. Next is oxidation state. Oxidation state. Next is oxidation state. Okay. Oxidation state. Okay. Oxidation state. The element of group 13 has 3 valence electrons. Okay. The elements of group 13 have have three valency, have three valency, electrons, three valency electrons, okay? NH2 NP1, NH2 NP1, NH2 NP1, okay? And ground state, NH2 NP1, that is S, and that is P plus 1, oxidation state, okay, excited state. NS1 NP2, okay? sp2 hybridization, sp2 hybridization, okay? sp2 hybridization, that is plus 3 oxidation state, plus 3 oxidation state, plus 3 oxidation state, okay? Group 13 elements show variable oxidation state of plus 1, plus 3, plus 1 and plus 3, have lighter elements plus 3 oxidation state. For lighter elements plus 3 oxidation state is more stable than plus 1 oxidation state, but for heavier element plus 1 oxidation state is more stable than plus 3 oxidation state, okay? They also an oxidation state plus 3. This oxidation state arises due to involvement of the electrons in NH2NP1 orbitals, which is called group valency, G. Plus 1 state arises due to involvement of NP1 plus 1 oxidation state is arises plus NP1, okay? NP1 to involve of NP1 and non-participation of NP2, NH2 electrons, and is termed G2 state. The heavier element tend to form univalent compounds, hence univalent Thylous compounds represent the most stable oxidation state plus 1. This is due to the fact that 6s2 electrons not participate into bonding because the energy required to unpair them is too high, okay? This is the phenomena of inert pair effect, which is shown by the heavy elements in the P block. Actually, it is not divalent since the structure of gallium chloride is shown as, okay? Gallium chloride. Gallium chloride is shown as Gallium plus gallium chloride minus, which contains gallium iodide and gallium first and gallium third. Okay. The stability of a plus 3 state is lower for heavier metals because delta S, delta HS for metals on solid state is metal to gas state is very high, and this is not compensated by the energy released in the formation of 3 bonds which are predominantly covalent. Okay, and predominantly covalent. Okay, inert pair effect. 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 This effect is prominently displayed by the p-black elements. Heavier p-black elements do not form cations according to their group number alone. They form cation in a lower oxidation state also 2 units less than that of group number. Since 2 electrons NH2 of the valence shell do not participate in cations formation, such electrons pair is called inert pair, and chemical effect which they produce due to non-participation is called inert pair effect. The S electrons in the other shell of the heavier members, tellurium, lead, bismuth, and pollen, remains paired and fail to participate in bonding because the energy required to unpair them is very large. These inert pairs are the valence electrons pairs of s orbitals, and their more stability is released to joining energy. Due to inert pair effect, elements generally exhibit to oxidation states. One group number oxidation state group and other lower oxidation state equal to G2. Okay. Example: 3 oxidation state is common oxidation state for group 13A. Okay. 3 oxidation state, 3 oxidation state, 3 oxidation state, 3 oxidation state for group 13. Group 13, third A. Elements, but they show +1 oxidation state. Elements, but they show +1 oxidation state. +1 oxidation state. +1 oxidation state. Okay. Also. Okay. As we move down the group from boron to thallium, as we move down the group, from boron to thallium, +1 oxidation state becomes +1 oxidation state, +1 oxidation state becomes becomes more and more stable. More and more stable. As we move down, the group from boron to thallium plus 1 oxidation state becomes more and more stable. This is due to gradual increase. This is due to gradual increase in inert pair effect in inert pair state. Inert pair effect from boron to thallium. Okay. Thus, thallium is more stable than thallium plus. Thus, thallium is more stable than thallium plus 3 ions. Okay. That is why the compounds of thallium are more stable. Thallium first are more stable than those of thallium third ions. Okay. Plus 3 oxidation state is common oxidation state for group 13A. Elements बढ़ते so plus 1 oxidation state also. As we move down the group from boron to thallium, plus 1 oxidation state becomes more and more stable. This is due to gradual increase in inert pair effect from boron to thallium. Thus, thallium plus 1 is more stable than plus thallium plus 3 ions. That is why the compounds of thallium first are more stable than those of thallium third. 5-year P black elements which in addition to their group number oxidation state G also show lower oxidation state given in brackets equal to G2 and second point. Okay. Second point. Group 14A. Group 14A elements are 6 elements. In this group, carbon and silicon show plus 4 oxidation state. In this group, carbon and silicon show plus 4 oxidation state. Whereas gallium, stainless and lead so both plus 2 and plus 4 oxidation states. Plus 2 and plus 4 oxidation states. Okay, the stability of +4 oxidation state. The stability of +4 oxidation state decreases and that of +2 increases from gallium to lead. Okay, in this group carbon and silicon show +4 oxidation state, whereas gallium, stainless and lead show both +2 and +4 oxidation state. The stability of +4 oxidation state decreases and that of +2 oxidation state increases from gallium to lead. Okay, the inert pair effect is greater in heavier elements in the same group. Both stainless and lead belong to group 14 of PT, but lead is heavier than stainless. The inertness of S pair in lead is greater than that in stainless. So lead +2 compounds one more stable than stainless +2 compounds. Also lead +2 compounds are more stable than lead +4 compounds. This is the reason that lead +4 compounds has the tendency to convert into lead +2 tetravalent lead. Lead +4 is an oxidizing agent. Example, lead oxide. PbO2 is work as a lead agent. Work as a oxidation agent. Okay, then Pb +4 +2 electron that is Pb +2. Okay, in tin stainless +4 is more stable since the inertness of S pair electrons is comparatively smaller, so this pair of electrons have a greater tendency to participate in bond formation. Thus stainless +2 changes into stainless +4 by losing 5s2 pair electrons. Okay, stainless +2 is stainless +4 +2 electron release. That is why stannous compounds are reducing agents. So stainless chloride is reducing agent. Okay, chemical properties of group 13 elements. First, oxides. All the elements of group 13 from oxides of the general formula M2O3. In oxides, the elements is +3 oxidation states. Okay, then M, metal, boron, aluminum, gallium, indium and thallium. +4M +3O2, that is high temperature. At a high temperature and 2M2O3. Boron forms boric oxides. 4b boron plus 3O2, that is 2b2O3. This is boric oxide. This is boric oxides. Boric oxides. Okay. Boric oxide is an acidic oxide which dissolve in base and form borates. B2O3 plus 6NaOH. That is 2Na3BO3 plus 3H2O. This is borates. This is borate. Sodium triborate. Borate. Okay. Alumina is obtained by heating aluminum in presence of oxygen. Al2O3. Alumina, Al2O3, 4 aluminum plus 3O2 after heating high temperature that is converted to Al2O3 obtained by heating. Al2O3 is obtained by heating aluminum in presence of oxygen. Okay. Al2O3 is amphoteric in nature, hence it is soluble in both acid and bases. Okay. Then Al2O3 plus 6HCl acid, that is after soluble 2AlCl3 plus 3H2O. Okay. And Al2O3 plus potassium hydroxide KOH, that is base. After soluble, this is converted into KAlO2 plus water H2O. This is potassium meta-aluminate. This is potassium meta-aluminate. Aluminium, Al2O3. Aluminium, Al plus 3O2 after in the presence of oxygen converted into Al2O3 at a high temperature, and Al2O3 plus HCl react with acid and change in AlCl3 plus 3H2O, and Al2O3 is react with potassium hydroxide to KOH base, and after reaction this is converted into KAlO2, potassium meta-aluminate plus water. Okay. And aluminum third oxides Al2O3 is known as alumina. This is alumina. Okay. It occurs in many allotropic forms. One of its allotropic form, corundum, is very hard and is used as abrasive. The basic character of these oxides increases with increase in atomic number. Okay. That is B2O3 acidic, Al2O3, Ga2O3 amphoteric, and In2O3, Tl2O3, that is basic. This is basic character increases increases. Basic character increases. Okay. Hence, on moving down the group, there is gradual change from the acidic to amphoteric and then to basic character of the oxides. Thallium also forms monoxides. Thallium oxide, which is more stable than Tl2O3, as Tl2O3 is less stable, hence it decomposes below at 373 Kelvin to Tl2O2. Okay, thallium oxide Tl2O3 at 373 Kelvin temperature. This is converted also in Tl2O plus O2. Tl2O plus O2. Acidic character of B2O3. Acidic character of B2O3 is due to its small size and have high charge density. Consequently, it tends to pull up electrons from water molecules, as a result of which oxygen-hydrogen bond breaks and proton H plus ion is produced. That is why B2O3 becomes acidic, but in case of Al2O3 and Ga2O3, they possess larger size, hence the breaking up oxygen-hydrogen bond is relatively smaller, hence their oxides are amphoteric in nature. Okay, hydrides, hydroxides, second chemical, hydroxides, okay, hydroxides. Boron and aluminum form hydroxides. Hydroxides of boron which is boric acid, H3BO3 or BOH whole thrice. Okay, BOH whole thrice is Fairly acid. It dissolves in strong alkalis, forming metabolites. Then boron, OH whole thrice, BOH whole thrice plus sodium hydroxide is NaBO2 plus 2S2. Okay. Aluminum hydroxide is obtained when an alkali solution is added to a solution of an aluminum salt. AlNO3 whole twice plus 3NaOS is AlOH whole thrice plus 3NaNO3. AlOH whole thrice is amphoteric in nature. It dissolves both in acid as well as in bases. Okay, action of acids. Action with acids. Action with acids. Boron does not react with hydrogen chloride but is oxidized by nitric acid and sulfuric acid to boric acid. Okay, boron plus 3 nitric acid, that is converted as 3BO3 plus 3 NO2 nitrogen dioxide, and boron plus sulfuric acid, that is converted into 2H3BO3 plus 3SO2. Aluminum, gallium and indium react with nitric acid and sulfuric acid as follows. M plus 6HNO3 is MnO3 M plus 6HNO3, that is MnO3 whole thrice plus NO2 plus 3H2O. Okay, and 2M plus 6H2SO4 is M2SO4 plus whole thrice plus 3SO2 plus 6H2O. Thallium react with nitric acid and sulfuric acid and forms univalent thallium plus nitrate and sulfates. Okay, Tl plus 2HNO3, that is TlNO3 plus NO2 plus H2O, and 2Tl plus 2H2SO4, that is Cl2SO4 plus SO2 plus 2H2O. Fourth point, highlight. Highlights. The elements of group 13 react with halogen to form trihalides of the type of MX3, where M is boron, aluminum, gallium, indium and thallium, and X is halides. The element of group 13 react with halogen to form trihalides of type of MX3, where M is boron, aluminum, gallium and indium, and X equal to, that is and thallium, and X equal to fluorine, chlorine, bromine, iodine. The boron trihalides BH3 compounds are covalent compounds formed by sp2 hybridization. The boron trihalides BH3 compounds are covalent compounds. Formed by sp2 hybridization. sp2 hybridization. Okay, and halides of boron are electron deficient compounds, and hence they can accept a pair of electrons and act as Lewis acid. F3b plus NH3, that is F3b NH3, and BF3 plus F negative, that is BF4. Okay, fluoborate ion. This is fluoborate ion. Fluoborate ion. Fluoroborate ion. Okay. The halides of boron and aluminum undergo hydrolysis reaction. Undergo hydrolysis reaction. Hydrolysis reaction. BF3 plus 3H2O. That is H3BO3 plus hydrogen fluoride HF and BCl3 plus 3H2O. That is H3BO3 plus hydrogen fluoride and AlCl3 plus 3H2O. That is AlOH whole thrice plus 3HCl. Okay, 3HCl. Hydrogen fluoride. Hydrogen fluoride. Hydrogen fluoride. Hydrogen fluoride. The fluoride of aluminum and gallium, indium and thallium are ionic and have high melting point. The other halides are mainly covalent when anhydrous. The fluoride of aluminum, gallium, indium and thallium are ionic and have high melting point. The other halides are mainly covalent when anhydrous. Alumina AlCl3, aluminum bromide AlBr3 and gallium chloride GaCl3 exist as Denmark. Okay, due to which they attain octet of electrons. The dimeric structure remains as such in nonpolar solvents such as benzene or ether and carbon disulfides. It breaks up into M6H2O plus 3 and X negative ions due to large here of hydration. These halides are found by sp2 hybridization. Hence the halides possesses triangular planar structure in which M is present in the center of trigonal. M is present in the center of the trigonal. The halides of boron are monomer, whereas other halides exist in a dimeric form. The structure of AlCl3 whole thrice or Al2Cl6 is given. You can show aluminum, chlorine, okay, chlorine. And AlCl3 occurs as Al2Cl6 in the vapor state having a bridge structure. The arrow indicates donation of electrons by chlorine atom. Okay, chlorine atoms. Okay, and the covalency of aluminum increases to +4. The chlorine atoms are arranged tetrahedrally around each aluminum atom. AlCl3 is used as a catalyst. In organic chemistry. Friedel-Crafts recreation. Okay, it is hydroscopic in nature and fumes in moist air due to formation of hydrogen chloride. Okay, then 2AlCl3 aluminum chloride plus 6H2O, that is 2AlOH whole thrice plus 6HCl. Okay, thus AlCl3 removes electron deficiency by dimerization. Thus AlCl3 removes electron deficiency by dimerization. Okay, Al2Cl6. Due to coordinate bond between aluminum and chlorine, electron deficiency is removed. Okay. Next, relative strength of trihalides of boron and Lewis acid. Relative strength of trihalides of boron and Lewis acids. Okay, Lewis acids. The relative strength of trihalides of boron to accept a pair of electrons and thus to act as Lewis acid on the basis of steric concept and electronegativity concept of fluorine, chlorine, bromine and iodine should be in order given below. BF3 is greater than BCl3 is greater than BBr3 is greater than BI3. Okay. On the basis of heats of formation data and by studying infrared spectra, the relative electron pair acceptor strength of these halides is in the order of given below. On the basic heats of formation data and by studying infrared spectra, the relative electron pair acceptor strength of these halides is in the order given below. BF3 is less than BCl3 is less than BBr3 is less than BI3. Okay, and this is on the basis of heats of formation data and by studying infrared spectra, the relative electron pair acceptor strength of these halides is in the order given below. Okay. This can be explained in terms of back donation of electrons from halogens atom to boron atoms. Okay. BX3 are covalent compounds in which sp2 hybridization takes place. 3 sp2 hybrid orbitals overlap with 3 singly filled p orbitals of fluorine atoms, giving rise to the formation of BF3 molecule. Okay. Then boron as ground state boron as ground state 2s and that is 2p. B excited state, boron on excited state, boron on excited state is converted into sp2 hybrid orbitals. This is sp2 hybrid orbitals. Okay. Sidewise lateral overlap of the vacant 2p orbitals of boron with one completely filled 2p orbitals of fluorine occurs, due to which p pi bonds is formed between boron to fluorine, and that is why BF bond acquires some double bond character. This type of bond formation is known as back bonding. This is given in this figure. You can show also in this figure. This is a boron, fluorine. This is fluorine, and this is converted in boron. This is fluorine, and fluorine, bromine, fluorine. Okay. Phenomenon of back bonding in BF3 molecule. Phenomenon back back bonding in BF3 molecules. BF3 molecules. Okay. Since any one of three fluorine, chlorine, bromine, iodine atoms can take part in back bonding, the structure of BF3 can be visualized as a resonance hybrid of the following structure is given. You can show fluorine plus, that is bromine negative, fluorine, that is fluorine, bromine, that is negative, fluorine plus, and fluorine, that is fluorine, bromine negative, that is fluorine, that is plus 1. Okay, this is various probable structures of BF3 molecule involving back bonding, As a result of back bonding, the electrons deficiency of boron is partly compensated, due to which the Lewis acid character of BF3 is reduced. The tendency to form a p-pi bond is maximum in BF3, and it decreases as we move to BCl3, BBr3 and Bi3. Thus, Lewis acidity shows the increasing trend as BF3 is less than BCl3 is less than BBr3 is less than Bi3. This can also be explained as follows. The structure of BF3 is given: X plus double bond, B minus, and X. Okay. The effectiveness of B negative double bond X positive decreases from fluorine to iodine due to increase in size from fluorine to iodine. Due to increase in size from fluorine to iodine, thus magnitude of negative charge on boron decreases from chlorine to chlorine, and hence approach of negative as increases from BF3 to Bi3. The acidic strength increases from BF3 to Bi3. The acidic strength has the order of BF3 is less than BCl3 is less than BBr3 is less than Bi3. Okay. Relatively acid Lewis acid strength of halide of group 13 elements. Relative Lewis acid strength of halide are group 13 elements. Okay. Relative Lewis acid strength of halides of group 13 elements. As we move down the group, size increases, due to which the electron pair acceptor ability goes on decreasing in the order boron is greater than aluminum is greater than gallium is greater than indium is greater than thallium. As we move down the group, as we move down the group, size increases due to which the electron's pair receptor ability goes on decreasing in the order. Boron is greater than aluminum is greater than gallium is greater than indium is greater than thallium. BF3 AlCl3 accept lone pair of electrons from donor atoms like sulfur, oxygen and nitrogen etc. and behaves as Lewis acid. Next 5.5 hydrides. Hydrides. Okay. Boron forms several volatile. Boron forms of several volatile hydrides. Example B2H6, B4H10. Gallium forms of volatile Ga2H6. Aluminium or non-volatile AlH3 probably polymerized, while indium forms a solid salt-like hydride with atomic hydrogen. Hydrides, first point. Hydrides of boron. Hydrides of boron. Okay. Hydrides of boron having general formula BnHn plus 4 and BnHn plus 6. Okay. Diboron B2H6 tetraboron B4H10 pentaboron B5H9 B5H11 and hexaboron B6H10 and decaboron B10H14. Okay. Decaboron B10H14. It may be noted that BH3 is not known. BH3 is not known. BH3 is not known. It is electron deficient compound and dimerizes B2H6. The hydrides of boron are known as boranes. The hydrides of boron are known as boranes. The hydrides of boron are known as boranes. When boride is treated with a dilute acid mixture of boranes is produced. Main product is B4H10 and B2H6 traces Mg3B2 plus 6HCl, that is B2H6 plus 3MgCl2 and 2Mg3B2 plus 12HCl, that is B4H10 plus 6MgCl2 plus H2. MgCl2 plus H2. Okay. Hydrides of aluminium. Hydrides of aluminium. Okay. Next, hydrides of aluminium. Hydrides of aluminium. Hydrides of aluminium. Aluminium. Okay. All forms of non-volatile polymeric hydride of formula AlH3X, which is called alans. Okay. It consists of AlH2Al. That is bridge structure. Bridge structure. Okay. Third point. Gallium forms of GaH3, which is known as gallium, and dimerizes to a volatile Ga2S6. Okay. Gallium forms GaH3, which is known as galen, and fourth point. Indium forms of polymeric hydride like INH3N, but thallium hydride is very unstable. Boron, aluminium, gallium also forms complex hydrides like lithium borohydride, LiBH4, lithium alumina hydride, LiAlH4, and lithium gallium hydride, LiGaH4. Okay, these hydrides are strong reducing agents. Reducing agent. Oxy acids. 6 point. Oxy acids. In the solid state, boric acid exists in 4 different forms. Orthoboric acid, H3BO3, orthoboric acid. HbO2, metaboric acid, metaboric acid, and H6B4O9, that is polyboric acid, and H2B4O7, that is tetraboric acid. Okay. H3BO3, orthoboric acid, HbO2, metaboric acid, H6B4O9, polyboric acid, and H2B4O7, tetraboric acid. But in aqueous solution, meta and tetraboric acid are converted into orthoboric acid. Hence, out of these, orthoboric acid is the most important acid. Boric acid is prepared from selemanite mineral. Okay, selemanite mineral. Ca2B6H11 plus 2SO2 plus 9H2O, that is converted into calcium, CaSO3 plus 6H3BO3. It is also obtained from borax. Na2B4O7 plus sulfuric acid H2SO4 plus 5H2O. 5H2O. That is Na2SO4 plus 4H3PO3. Boric acid is very weak acid. Boric acid is very weak acid, and temperature is 6 multiply 10 to the power minus 10 Kelvin, and is treated as Lewis acid because it accepts electron pair upon heating. Ethoric acid B2O3 is obtained. Then H3BO2 ortho at 100 degrees Celsius temperature. HbO2 meta after at 140 degrees Celsius. H2B4O7 pyrotetra and red heart temperature. Red heart, that is converted B2O3 oxides. Okay. All alum formation. Next is alum formation. Alum 7-point alum formation. All elements of group 13 form alum following types of except boron. That is M2SO4, M-2SO4 whole thrice into 24H2O. Okay, where M is a univalent metal ion. Where M is univalent metal ion, and M2 dash is a trivalent metal ion. Trivalent metal ion. Example K2SO4. Example K2SO4 Al2SO4 whole thrice into 2H2O into 24H2O. That is potassium. Potassium. Okay. Next 8 point. Action with air. At normal temperature, pure boron does not react with water. Boron is unreactive at normal temperature. It only reacts with heated upon combustion. With air, boron gives B2O3. Aluminum reacts radially in air at normal temperature and forms a protective layer of the oxides on its surface. 9 point. Action of water. At normal temperature, pure boron does not react with water. Ammonium decomposed cold water. Gallium and indium do not react with cold or hot water. And thallium is little reactive by water and forms an oxides layer on the surface. 10 points. Nitrites. Action of water. Aluminum normal temperature. At normal temperature, pure boron not react with water. Aluminum decomposed cold water. Aluminum decomposed. Aluminum decomposed at cold water. And gallium indium do not react with cold or hot water. And indium and gallium, not react with cold or hot water, okay? And helium is little reactive by water and forms an oxide layers on the surface, okay? And next is nitrites, okay? All elements of group 13 combine with nitrogen and form nitride of type of Mn except thallium, okay? And all of these are stable and hard. They produce NH3 gas by steam, okay? Then 2b boron plus nitrogen at a high temperature, that is 2 Bn, okay? And aluminum plus nitrogen, that is normal temperature, that is 2Aln, and Br plus 3H2O, steam, that is H3BO3 plus NH3, and Al plus 3H2O, steam, that is converted in AlOH all thrice plus ammonia gas. Complexes and organometallic compounds. Okay? Complexes, 11 point. Complexes and organometallic compounds due to high ionic potential of M3 plus and electron deficient nature of MS3, complexes are found by M3 plus cation, okay? MaBH4 LiBH4, that is BX4 negative, AlF6 whole thrice negative, etc. Okay? BX4 are tetrahedral, and AlF6 3 is octahedral, okay? Group 13 elements form complexes more easily than the S block elements due to their smaller size and have high value of plus B charge. They form complexes like gallium Cl3, indium Cl6 whole minus 3, and Tl Cl6 whole minus 3. They also form octahedral complexes with chelating ligands as acetylacetone, oxalate, and ethquinoleonatrate, okay? All trihalides of group 13 combines with general reagents and organolithium reagents forming trihalides or trial compounds, okay? BF3 plus 3C2H5 MgL, that is BC2H5 whole thrice plus 3 Mg IO. AlCl3 plus 3CH6 Mgi, that is AlCl3 whole thrice plus 3 MgICl. GaCl3 plus 3C2H5 Li, that is GaC2H5 whole thrice plus 3 LiCl. InBr3 plus 3C6H5Li, that is indium C6H5 whole thrice plus 3Li Br. Okay? The synthesis of argon-aluminum compounds from aluminum metal and hydrogen in presence of Giler catalyzed aluminum alkyl is very important. Al plus half H2, that is 2Et3 Al, and arrow mark of 3Et2 Al S. Okay, next comparison between boron and aluminum. Okay.